and we have told to you to stop. But anyway, we'll go ahead with copyrights, patents, other IPR requirements at DYPCOE. So thank you very much, sir, for giving the insight of IPR.
Thank you, sir.
Third speaker of this session, Dr. S. Pradyumna, Professor, Department of Applied Mechanics, IIT Delhi. He is Outstanding Young Faculty Fellow awarding at IIT Delhi in 2011. He has recipient of National Postdoctoral Fellowship from AICT New Delhi. He received Young Research Travel Grant in 2008 and he has attended Srimani University, Japan. He is Secretary for 3rd Asian Conference on Mechanics of Functional Materials and Structures in 2012, which is held at IIT Delhi. He has participated in various conferences, workshops, short-term courses, national programs at various organizations including IIT Delhi, IIT Kharagpur, IIT Roorkee. He has invited at different forums, including Bapatla College of Engineering, Andhra, to deliver the expertise available with him in mechanics and especially in finite element. And today he is going to talk upon the topic analysis of constant and variable stiffness composite panels. So I am requesting Dr. Pradyumna sir to start with his lecture. Sir. Hello, sir.
Hello. Hello, I'm audible?
Yes, sir, you are audible.
Okay, just I'm sharing my presentation now. Let me share the presentation.
Yes, sir.
Hello, sir. Pradyumna, sir.
Yeah.
You have 25 minutes for your presentation.
My slides are visible now?
Not yet.
Let me share it again. Is it visible now?
Yes.
Okay.
Just put it in presentation mode, sir.
Yeah, I'm trying it. But
yes.
Yeah, just a minute. Is it okay now?
Yes, sir. Yes, sir. Presentation mode, sir.
Yeah, it's in presentation mode. Can you see the slides?
No, sir. Sir, put it in slideshow.
Yeah, that's what I have done. Is it visible now?
It is visible. If you can.
Yeah. When I go into the slideshow mode, it is not visible, I believe. Is it visible now?
Yes, it is visible. You can.
Sir, okay, can you choose the view option? Can you choose the view just to the left side?
You may continue with this, sir, because I think there is a compatibility for Windows and Mac system.
No, yeah. Mac, I'm using this keynote for this. Anyhow, I'll continue my presentation without wasting time.
Visible.
Yeah. Good morning, everyone. And sorry.
Yes, sir. 20 to 25 minutes.
Okay, yeah, I'll try to make it in before that. Yeah. Okay. Thank you, Professor Shekhar and the team of DY Patil College, giving me this opportunity to present my work. And it's very difficult in these times to just, it's a good way of keeping in touch with our colleagues in other colleges and the research fraternity. So my topic for today is on analysis of constant and variable stiffness composite panels. So I briefly talk about the variable and constant stiffness panels, but my focus is on the composite structures, right? And also my student Ms. Ankita Gupta is has contributed on this on variable stiffness and constant stiffness panels. Okay, so let's move on with this. So as many of you are aware that the composite materials consist of a combination of materials that are mixed together to achieve a specific structural properties. Maybe you require more stiffness in a particular direction and lesser in another direction, you can do so, right? The properties of the composite are superior to the properties of the individual materials from which it is constructed. Like for example, I have a carbon fiber, and when it is mixed with epoxy or a matrix, the combined property is superior compared to the fiber as its own or a bulk property. So therefore, a mixing of two different materials has a different advantage. Composite materials you have seen in many industrial applications like automobile, aerospace, civil, and medical applications. The benefits of composites is that it is cost effective. I'm not saying it's cheap, it's cost effective. The weight is an issue because in satellite structures and in aerospace structures, you want to reduce the weight of the structure. So therefore, this is a lightweight structure. So you can use the same structure for getting the lightweight structure. It has got more strength and stiffness. I'll come to the strength and stiffness a bit later. And it offers corrosion and wear resistance. So which is typical of metal to undergo corrosion and wear and tear. So with the use of composites, we can avoid some part of corrosion and wear resistance. It has got a good fatigue life and thermal and acoustical insulation. In many applications we have seen using for thermal and acoustic insulation. And thermal conductivity is one part, and the most important part is the tailored finish. So you can tailor it depending on what is the objective of your design, what is the objective of your applications. You can tailor make these structures, and not like metallic structures. These structures are non-magnetic because there is no problem of magnetic attraction. But however, there are some limitations to these structures. Please let me know if I'm not audible or any problem. I'll okay. I hope everything is.
Yes, it's fine.
Okay. So there are
slides are not changing. Slides are not changing. That's why I just wanted. So, are you changing the slides?
Yeah.
Only first slide is visible.
Really? I'm at a slide which shows the limitations of the.
No, it is showing as a first slide only. So that's
okay.
Fine.
Now, otherwise I'll go with this mode on. Now is it visible?
Yes, correct. Okay.
Okay, I'll proceed with this. Yes. I'll proceed with this mode in that case. Yeah.
Yes, correct.
Okay. However, there are certain limitations to these type of structures. The cost of raw materials and fabrication is very high because the materials are the cost is high, and also it requires a certain level of skill for the laborers to install this. For example, you take concrete or you take a steel or any metallic structures. It's very easy to fabricate it and easy to assemble. But when you come to the composite structures, it requires a certain level of tools, certain level of machinery, certain level of skills. So that is very difficult and expensive too. And the transverse properties of these are weak. Transverse properties is when you consider a fiber, the direction of the fiber, you call it as a longitudinal direction, and perpendicular to that, we call it as transverse properties. These are weak. The fibers and matrices are the two components in a composite. The matrix is weak, having low toughness. It's very difficult to reuse, or disposal is very difficult. Repair is very difficult. It's introduced new problems. The material requires sophisticated transport and storage facilities. And curing is also a big problem. And finally, the matrix which we use to bind the fibers is subjected to environmental degradation. So with all these limitations also, we prefer composite structures in different industrial applications. For example, if you go to this, these are some of the applications of composite materials. It's widely used in aeronautical. You can see what type of fibers are used, what type of composite is used in an aircraft structure. Carbon laminate, carbon sandwich, fiberglass, aluminum, lot of materials mainly used are the composite structures, right? In civil engineering industry also, people use composites for retrofitting of the structure. If you have an old structure, you want to repair it, you want to strengthen it, you can use the composite structure. So people have used the composite sheets or the fiber sheets to retrofit the columns and beams to strengthen the structure. And in marine industry also, you can use the decks of the slabs and of the ship. And in many places, people can use these composite structures. You are well aware of the fact that in automobile industry, many cars nowadays, the super fast cars you are getting, the body is made of the carbon fibers. Even in sports industry, biomedical industry, people use composite structures, carbon fibers, and matrix. These are some of the applications of the composite materials, right? Now I move on to the types of composites. The types of composites are broadly three. One is the fiber composites, in which you have fibers which are bonded together by a certain matrix. Next, you have a laminated composite. You get more than 2 layers of composite materials which are glued together to make a laminated composite. In a particulate composite, what we do is the particles of metals or any stronger material are taken as a particulate or a powder form and mix it with some matrix. So that gives us a particulate composite. In nature also, you can see different types of composites with different strength characteristics and so on, right? The fibers, the primary function of the fiber is to carry the loads along the longitudinal direction. Fiber, you can see a jute fiber in the natural composite or anything. It mainly carries the load in the longitudinal direction. It is very weak in the transverse direction. So therefore, we predominantly use this to carry the axial loads. The common fibers are either made of aluminum, beryllium based, carbon fiber based, molybdenum, or metal like steel, aluminum, and different metals can also be contributed as a fiber. So when I come to the matrix part, what is the function of the matrix is to transfer stresses between the fibers. If you have two adjacent fibers, that they're sorry. Any issue? Somebody speaking?
Mr. Vaibhav, please mute yourself.
Okay. A basic requirement for a matrix material is that the strain at break must be larger than the strain for the fibers it is holding. That is because the failure is actually has to be a ductile failure rather going for a brittle failure. If the fibers fail first, the matrix suddenly fail and the whole structure collapse. To avoid this, we assume that the matrices are failing first, then you get some sort of warning so that you can retrofit or repair the structure. And the matrix should have low coefficient of thermal expansion. We should also have good flow characteristics so that it uniformly mixes with the fibers. Therefore, the matrix also has certain characteristics. Now, let us come to the strength part of the fiber. I have listed here different Young's modulus, specific gravity of the fibers which are widely used, like graphite fiber, Kevlar fiber, glass fiber, and also with steel and aluminum. These are the two popular metallic fibers we use. Now, if you observe that the Young's modulus varies from fiber to steel. For example, steel has a very high Young's modulus compared to these kind of fibers, which has got 85, 124 and so on. But if you take the ratio of its Young's modulus to density, then you see the numbers. So that means Kevlar fibers and steel, if you compare, Kevlar fibers are better when you take the E by rho or the Young's modulus to density ratio. So that means for a lighter load or the light weight of the structure, you can get a bigger strength, which is also provided by the metallic structures. So these are the things we call it as the strength to weight ratio or strength to stiffness ratio. Okay, so these are the superior properties of the fibers which are worth looking at while constructing a structure which can be composite, right? Now I come to the mechanics part of the composites. The mechanics of composites has two parts. One is the micromechanics, in which we study the behavior of the composites, where the interaction of the constituent material we examine in a microscopic scale. Now that means the behavior or the interaction of the fiber with the matrix, or the properties of the fiber we know and the matrix properties we know. How does the composite property can be derived with these properties is a part of the micromechanics. So our job is to find the average properties of a composite from the individual properties of the constituents. So that we can do with the help of micromechanics, right? And second is the macromechanics. In macromechanics, what we do is we develop the stress-strain relationship for a unidirectional, bidirectional lamina. Okay, so the loads we apply in the principal direction so that there is no mixing of the normal and the shear stress taking place. So that is one part. So our job is to develop the relationship for stiffness, thermal coefficient, moisture, and other strength related aspect that we do using the macromechanics. And also we develop the failure theories, like the failure theories we have for steel, which many of us have studied in strength of materials. So the same type of theories can also be developed for the composite. Now, coming to the lamina, so we are using this lamina, laminate, and so on for some time. What is a lamina? We have a lamina as a basic building block. What we do is we take some fibers in a unidirectional fiber, or it's a bidirectional fiber. It is actually bonded with a matrix. This is one particular layer of a flat arrangement of unidirectional fibers or oven fibers in a matrix. If I keep on stacking one lamina on top of another, I get a laminate. So laminate is actually a plural. So it's a stack of lamina. We call it as laminate. So the sequence of this orientation of the fiber, we call it as a lamination scheme. Now next, what we call it, we go to the ply orientation. Ply orientation is the direction of the fiber. So what is the job of this? Now, for example, if I want to carry the longitudinal loading, so we go for the zero ply orientation. Zero ply means it is along the application of the axial load. The fibers are stronger in the longitudinal direction, so it can carry more load in the longitudinal direction. So therefore, we prefer zero ply orientation to carry the longitudinal direction. 90-degree ply, that means it's perpendicular to the 0 degree. So that means it can carry more transverse load because the 90 ply orientation is the axial loading for the transverse load. Therefore, it can carry the more load. Plus or minus 45-degree orientation for shear loading. So in order to minimize the in-plane shear, place the 45 and minus 45 plies together. So what happens in that case is, you know that in strength of materials we have studied, when I apply a longitudinal load, the 45-degree will have the principal stress, principal direction. So therefore, that is the optimum way of looking at it. So in that case, what happens in case of in-plane shear, you have tension and compression, as it's a pure shear case. When I have only the shear stress acting on an element. So if I rotate it by 45 degree, so the pure shear can be represented only with the help of a normal stress, which is tension and compression. So this is a basic we have understood in the strength of materials. So the other part we are looking at is to minimize the warpage and interlaminar shear. So we have to maintain the symmetry. Otherwise, what happens, we'll see later. Okay. Next, we go to the constitutive equations. What is a constitutive equation? Is, for example, it's a relation between the stress and the strain. it characterizes the individual material and reactions to applied loads and are called constitutive equations. So what happens is, in case of an isotropic material, the definition of isotropic material is every material properties in all directions at a point are same, isotropic. If they are different, we call it as anisotropic plane. So in case of an isotropic which has got equal material properties in each direction, so you apply the normal stress, you just stretch it, it undergoes only stretching or the axial deformation. But if it is anisotropic material, so when you stretch, it undergoes shear. So this is the beauty of the anisotropic material, and it makes things complex so that you can do a rigorous analysis for that. And vice versa, when you apply a shear stress, the material undergoes stretching also. So this is the property of the anisotropic material. So the Hooke's law connects all these properties. Hooke's law is all familiar with the Hooke's law. This is for an isotropic material. When I want to write the strain in an x direction, I use the stress in x, y, and z direction and use the Young's modulus and Poisson's ratio. So in all these, I only require the Poisson's ratio and the Young's modulus. Only two independent material constants are required in case of an isotropic material. But things will change when it becomes anisotropic. So when it becomes anisotropic, I require 3 to the power 4 number of elastic constants. But I cannot go for that big number. I make some certain simplifications. I assume the material as orthotropic material. So what's an orthotropic material is that if there are two orthogonal planes of material property symmetry, that means for any direction if you go, two mutually perpendicular directions or the planes will have the same or the same material property with relative to the third mutually orthogonal plane. We call it as orthotropic plane. In this case, there is no interaction between normal stress and the shear stress, right? And another simplification we make is transversely isotropic. If at every point of material, there is one plane in which mechanical properties are equal in all directions. For example, I take any point here, any plane, at least I get one plane here in which all the material properties are same, then I call it as transversely isotropic. So in that case, I only get 5 constants. So it becomes easier for analysis, right? So therefore, we get from anisotropic, we make it orthotropic, from orthotropic to transversely isotropic. So from there, you can further simplify and get 5 constants and solve the problem. Now we move on to the composite plates. So composite panels, plates or shells, these are widely used because if you take a fuselage of an aircraft, it's a shell panel. So to analyze the shell panel or a plate, we can use different strategies. Like we have two-dimensional analysis where you have classical theories and shear deformation theory, 3D elasticity theories. In that we have 3D elasticity and layer-wise theories. There are different aspects in analysis. How this varies. Now, for example, I just take a simple case here. In this case, if I take this is a beam or a plate, you can assume. So when it deforms, this is the deformed shape of the structure. So what happens? This is the normal, which is the horizontal line, and the normal at this point after deformation is shifted by dw0 by dx. This is the slope. So what we assume here is this normal to the mid surface after deformation is actually normal to the mid surface here, and it remains straight. This is sorry. This is similar to our Euler-Bernoulli beam theory. And if you move further, this is straight but not perpendicular to the deflected mid surface. So this is the first order shear deformation theory. In the third order theories, what we do is we assume the deformation in a third order sense. So therefore, we can use it in a third order theories. Now I move on to the stress strain distribution. Because of our assumption, we know that the strain distribution along the layers is constant or continuous. But if you look at the stress distribution, there is some certain jump. So there is a mismatch of, or there is a discontinuity of the stress distribution across the thickness. So this creates some problem because when there is a mismatch in the stress, the plies will debond or there is a delamination and it becomes another problem. So to avoid this, people use different computation techniques to solve this. Okay, now I move on to the variable stiffness. The variable stiffness we can achieve from either changing the fibers from straight fibers to curvilinear fibers. We can change the stiffness, or we can vary the placement of this fiber or fiber volume fraction. We can vary the stiffness along the length, or we can increase the thickness or increase or decrease the plies in a layer. We can change the stiffness, or the other option is to provide stiffeners. So these are the different options we can have for changing the stiffness. So what is the advantage? It reduces the stress concentration around a hole or cutout. It improves the load bearing capacity or the buckling response of the structure. So we get some innovative design possibilities with respect to the curvilinear fibers. We can also optimize the weight of the structures with the help of variable stiffness. This is how it varies. Now, for example, the origin is at the center of the plate. If I change, T0 is the angle of the fiber here, and T1 is the angle at the edge of the plate. So we can vary the angle as a function of x, and we can use this theta as a function of x in the analysis. So we represent this as T0, T1. So there can be many number of layers in this. So that varies the direction. So we have this type of formulation, zigzag theory. This is part of third order theory or the layer wise theory. So there are different options for zigzag theories. So these two are the zigzag theories. Now coming to the zigzag theory coordinate system. Sorry?
Sir, the control kara.
Okay, Z0 K is the coordinates we are measuring from the midplane of the plate. ZK is the coordinate we are measuring it from the center of the any particular kth layer. So this actually is our Murakami zigzag based function. So when this ZK can vary from minus HK by 2 to plus HK by 2. Essentially, this varies from -1 to +1. So this is how the displacement, in-plane displacement U looks like. This is a constant U0. This is U1 is actually a rotation. It varies along Z. And this is a zigzag function. So it varies from -1 to +1, -1 to +1, depending on which ply we are looking at. So this adds to certain level of accuracy into our analysis. The stress strain relationship looks like this, which I already talked about. Q11, Q12, Q1, these are actually called as the stiffness coefficients of the kth lamina. We have 6 components of stress at a point, but we consider the plane stress condition. So the sigma z is vanishing. So therefore, we only have 5 components of stress, and we use a transform stiffness matrix. Transform stiffness because each layer having different orientation with respect to a global axis. So therefore, we have to get the transform matrix. We can get that transform matrix from these. So because every Q11 bar, Q12 bar is a function of theta, and we can obtain that with the help of a transformation relationship. So to roughly talk about this, it is similar to what we have done in case of a stress and strain transformation in our strength of materials. It's a similar approach and similar method is used. The only thing is you have 5 components of stress, right? And theta is function of x. So this is some kind of complicacy, but still it can be manageable, right? So these are the remaining terms U1, U2 to U7 which can be used. Now I go to the strain displacement relationship. We have used the strain of thick laminated shells provided by some Lisa and Chang in 1996, which can be used for thick as well as thin laminated panels also. If I make the radius of curvature infinity, Rx/Ry infinity, I get the plate. So it's a more general approach to solve both the cylindrical, spherical form of shells and plate. So therefore, it's a general approach. Now I come to the finite element formulation. So this is the last part of my presentation. Finite element formulation. We have used a 9-noded isoparametric element, because we can also use any convenient element which is available in the finite element library. We have written our own formulation for this. So we developed the stiffness matrix with the help of strain displacement relationship, the material properties, and we have integrated over the area of the plate, and we get the stiffness matrix. So this is all obtained from the principle of virtual work. So this is this is not a forum for this mathematical principle of virtual work. So I also get the mass matrix from the kinetic energy of the system, where rho is the mass density, n is the shape function of the system. So this is a typical dynamic equilibrium equation we get without any load. This is a free vibration problem. Mass into acceleration plus stiffness into the displacement is equal to 0. It's a typical dynamic equation. This is the typical 9-noded element we have used, and the corresponding shape functions are also given here. Okay, so we have performed some static analysis on 090 lamination, which is a constant stiffness fiber, and it also has got 3-layer, 4-layer, and we have non-dimensionalized the displacement as given by this. The simply supported boundary condition and the material properties are also given here. Now we can see how it compares. So we have used the higher order zigzag function and first order shear deformation theory, and these are the first order functions. The error, if you look into this, the error is huge because this is a first order result and we are using a zigzag theory. We have used different loading, the sinusoidally applied load, varying load, and the uniformly distributed load. And finally, what we have is, we have also analyzed constant and variable stiffness composites. And you can see that the results, what we have obtained with the help of zigzag theories, are better for both constant and variable stiffness constant and variable stiffness composites. To conclude, I can say that the constant and variable stiffness composites are used in wide applications. We have different analysis strategies available and research areas still open. People can venture into analyzing for different problems and design. In many engineering applications, the stress difference at interfaces are very important and require advanced analysis tools. So this area is still open, and many people are working and developing analysis strategies or design strategies and getting into new types of materials for better design of the structures. So that's all, and thank you very much, everyone.
Hello, Dr. Pradyumna, Professor.
Yeah,
yeah. You very nicely explain about the basic concept to the advanced concept of mechanics of composites and other things, mechanics. So really, we are very thankful to you, sir. Sir, I want to mention there are very few people in India, those who are working in this mechanics of composites and the continuum mechanics. So thank you for being with us, Professor Pradyumna. Thank you, sir. Thank you very much.
Thank you so much.